So my name's Alex Chircop. I'm a chief architect at Akamai and co-chair for the CNCF Storage TAG. I'll let my co-hosts introduce themselves.
My name is Raffaele Spazzoli. I work at Red Hat in consulting services.
My name is Xing. I work for VMWare by Broadcom in the cloud-native storage team, also one of the co-chairs of TAG Storage.
Brilliant. Okay, so what are we here for? We're going to be talking about the storage tag and how to be part of the community and some of the projects in this space. We're also going to talk about cloud-native storage and why this is important, and some of the new things that you should be looking at. And we're also going to talk about some of the white papers that we've been working on, including our landscape paper, the data on Kubernetes white paper, performance, and even some advanced topics like cloud-native disaster recovery. So you might be asking yourself, what is a tag? The tags are technical advisory groups, and we work and advise the TOC, which is the technical oversight committee that actually makes the decisions around the technical direction and the projects within the CNCF. There are 8 tags, and some of these work in specific verticals like storage or networking or runtime, for example, and some of these work horizontally, like, for example, the contributor strategy and the cloud-native security, which have a broader oversight across the projects. So you might ask who we are. So we're a number of coaches and tech leads, but fundamentally we're a very open community where you can learn, we can get advice, you can contribute to the cloud-native ecosystem. And we're a completely we're a very diverse group of people. So verging from independent contributors to project maintainers, builders, end users, platform engineers in this ecosystem. We're all available on the TAG Storage CNCF Slack group, or reach out directly if you have any questions. All of our meetings are open. We meet on the 2nd and 4th Wednesday of every month at 8 a.m. I'd love to see some of you in the calls. You can use the calls to find out about the projects that might be presenting, or ask questions or help contribute to white papers, or just take part in the discussions. So we talked about the tags advising the TOC. So what do we really do? Ultimately, it's all about helping the CNCF and the TOC to scale. And that is to scale the contributions, both in terms of the projects and the user community. And what do we mean by scale? You've probably seen from the keynotes that we have over 200 projects in the CNCF. It's growing extremely rapidly. In fact, we've had 19 new projects since Paris. And the rate of growth in the community is actually always accelerating. So you can kind of see the graph going up at a higher rate every month, with a lot of growth happening in sandbox projects. And in the scaling, we do 4 main things to help the TOC and the CNCF. The first and most important is around reviewing projects and doing project reviews. Each project in the CNCF is allocated to a tag. We do also then do a lot of work around education, doing working groups to generate white papers on the ecosystem and to help end users navigate and explore the storage ecosystem. Obviously, working with the user community is a big factor. We're always interested in hearing about new use cases and other challenges that you might be hitting, and how we can work with different projects to address those. And ultimately, providing subject matter expertise. So whether it's low-level file system information, or more broadly, how projects integrate with Kubernetes, for example. And we're talking about cloud-native storage, and why should you think about this? And ultimately, the answer is always, there's no such thing as a stateless architecture. We know Kubernetes running stateless workloads is obviously the its first mission in life, but ultimately we're in an environment where every application needs to store state somewhere, and those applications can use stateful services that live outside of Kubernetes, but more and more what we're seeing is users bringing those stateful services into Kubernetes as well. And the reason for this is because you've already done a lot of the work to make your workloads declarative. You've done the work to automate and have self-healing and failover in Kubernetes. And obviously Kubernetes is where you get your ability to scale horizontally and to increase the performance of these systems. So the question is, why would you choose then to do all of that work again in a different way, say with VMs or with other services in outside of the Kubernetes systems? And what we're here to say is, you know, cloud native storage is no longer actually that hard. There are a plethora of operators that enable you to run databases, message queues, key value stores, object stores, block storage, file systems, and a broad ecosystem and CSI support to integrate with the actual Kubernetes. And in fact, these are some of the storage projects which are part of the CNCF. We have quite a wide array here, from graduated projects, which include Rook, which is an operator for the Ceph project, Vitess, which is a very scalable MySQL alternative, Harbor, container registry, etcd, which you're all familiar with, which is the fundamental key value store for state in the Kubernetes control plane, TIKV, which is a very extremely scalable key value store. And then we have a number of incubating projects like Dragonfly and Longhorn, and kubefs, which is just about to go to a vote to move into graduation. And kubefs is an extremely distributed file system, which again is not a common thing, and it's really nice to see these additions to our cloud native ecosystem. Of course, all of these projects and more are listed under cncf.io/projects. And there's also a ton of sandbox projects, including projects that help with caching and machine learning and other workloads, which are going through the different incubation stages of the CNCF. And talking about those incubation stages, there are 3 main stages for projects within the CNCF. Sandbox projects are brought into the CNCF primarily to help build their community and to help the project mature. We focus on things like the IP policy, but there are also lots of experiments in sandboxes, and there's a relatively low bar of entry there. Incubation is where a lot of the due diligence happens, and this is where incubating projects are the projects which are being used successfully in production. And part of the diligence involves the tag and the TOC talking to production users or end users of those projects. And it's important to have, healthy governance and healthy project committers. And then graduation talks about is mainstream production use and adds on additional steps like having independent security audits and regular yearly reviews, as well as requiring committers from multiple organizations. One thing, I'm not going to go into a lot of detail here, but it's an interesting new resource. As we've been trying to scale the TOC and the tags, we're focused on creating a formalized framework for how we review the projects. So effectively giving projects a simple way of knowing immediately what type of questions are important. And these are the DTR, the domain technical reviews. And there are a number of questions that are general and then go into additional depth for each of the different verticals, and cover the planning phase around sandbox, the deployment requirements around incubation, and then more of the day two functions for graduation projects. So what I'll move on next is a little bit about the storage white paper. So one of the first things that the storage tag did was put together a storage white paper that explains the landscape and allows you to navigate and understand the different aspects of the landscape. We worked on, rather than defining sort of individual products or projects, we wanted to give end users the ability of like understanding how their application works and what attributes of a storage system are important to them. So we started off with defining the attributes of a storage system and then the different layers that make up the storage system, because cloud-native storage systems often have multiple components and multiple layers, as well as the, understanding the different types of storage types. So for example, we're covering both volumes, which might be block storage or file systems, as well as what we loosely call application API-driven storage, which might include object stores, key value stores, databases, etc. And finally, we also talk about the orchestration of these environments and some of the interfaces that allow you to integrate these storages with Kubernetes. We are working on finalizing version 3 of the white paper, and we obviously would love contributions and review. So a little bit about the storage attributes. We focused on having 5 main storage attributes, which cover availability, scalability, performance, consistency, and durability. And within those attributes, there are typically a number of different measures that we look at. So for example, availability might involve how does a storage node or a storage system fail over, but it might also talk about the data protection for things like replicas or erasure coding. Similarly, performance might be measured by latency or operations per second or throughput, and those different metrics might be important to different types of workloads. So for example, if you are very transactional focused, you might be focusing on the latency and the operations per second, but if you were, for example, operating a machine learning workload and you just need to ingest or process lots and lots of data, then the throughput might be a more important metric for you. And then we talked about the storage layers. So there are many storage layers, starting from overlay file systems and volume managers that might happen at the operating system or the host level. There are the ways that the storage systems might be deployed and the topology there. So you might have centralized, distributed, or hyper-converged. There are a variety of different data protection options, including the primary ones, which are replicas and erasure coding. And then advanced data services that the storage system might be providing, like replication or snapshots or clones. And last but not least, there's obviously the physical layer, because even in the cloud, at the end of the day, you're going to be hitting a physical layer, and that contributes to the overall attributes of your system. And it's kind of important to understand these different layers, because we often see, for example, file systems that might be built on object stores, so it might have some of the shared attributes of a file system, but it might have the latency functionality of an object store, for example. And we'll very briefly look at why this matters for a couple of different use cases and deployments, like hyperconverged block volumes and shared file systems. So when we look at the attributes, for example, of a hyperconverged, you need to think about availability in terms of your fault domains, because your compute and your storage nodes might be sharing the same resources, and a compute failure might result in a storage failure, or vice versa. Your performance might need to take into consideration that both your application workloads and your storage workloads are sharing the same backend network, for example. If we look at block volumes, we have a way of improving scalability with block volumes by effectively disaggregating the compute and the storage and allowing you to scale compute and storage separately. The availability with block volumes means that you can now move, you can typically move workloads between nodes, and the storage can follow. And when it comes to performance, you typically look at those block volumes to provide low latency, but ultimately all of that is also dependent on your network connectivity between compute and storage. Shared file systems similarly have a number of similar attributes where from a scalability point of view, shared file systems are all about how many nodes you can share the data across. But sharing data across lots of nodes then translates into consistency challenges, and you have to compromise between strong consistency and eventual consistency, because things like cache coherency and distributed locks are hard. And a lot of shared file systems could be built on many different layers, including block volumes or object stores, and that determines many of the attributes in your system too. And finally, object stores. So for example, when we look at object stores, we often think of object stores as providing an almost infinite scalability in terms of capacity and throughput, but latency is typically higher than, say, block volumes or file systems. And when we're looking at performance, you also need to think about the types of operations that you're doing within an object store, because the metadata operations might be the most expensive thing. And with that, I'll hand over to Xing, who's going to talk about running data workloads on Kubernetes.
Thanks, Alex. According to the 2022 survey by Data on Kubernetes community, more and more stable workloads are moving to Kubernetes. There are different types of workloads. Database workloads have the highest percentage, followed by analytics and AI machine learning. There's actually a latest report came out from DOK. I think database workloads still has the highest percentage. We collaborated with the DOK community on a white paper to describe the patterns of running data on Kubernetes. We described the attributes of a storage system and how they affect running data on Kubernetes. We compared running data inside versus outside of Kubernetes, and what are the common patterns and features being used while running data on Kubernetes. The paper was complete and published. Here we see that operators are managing different types of database clusters. The operator is the most commonly used pattern while running data in Kubernetes. According to the DOK survey, typically an organization would use more than one operator. On the operator hub, there are more than 300 operators. Among them, there are about 50 database operators. There are many common features and patterns being used while running data on Kubernetes. If you want to learn more about it, please read our paper. After finishing the paper describing the database patterns, we started to work on a new paper focusing on the running data analytics and AI machine workloads in Kubernetes. In this paper, we're trying to highlight the characteristics of data analytics and AI machine workloads and describe the patterns and trends in data storage to meet those new challenges. We're going to discuss data warehouses, data lakes, data cache, vector databases, and so on. Data warehouses and data lakes are typically used to store large data for analytics. Data warehouses typically store structured data. Data is usually cleansed and curated before entering the data warehouse. Traditionally, data warehouses use relational databases to store data. Modern data warehouses use shared object storage. Data lakes can handle a combination of structured, semi-structured, and unstructured data. Data lakes are mainly used for data analytics and AI machine learning. Data is typically stored in NoSQL databases such as Cassandra, object storage, or shared distributed file systems such as Hadoop, and so on. Data warehouses and data lakes are merging for many users. A data lakehouse is a hybrid of the two models. With the increasing popularity of data lakes and the disaggregation of compute and storage, we see that the compute layer is decoupled from the storage layer in both data analytics and AI machine learning. So data cache is playing a crucial role in accelerating data loading, minimizing data transfer between compute and storage, and reducing API costs, which is usually an overlooked aspect of accessing object storage. There are different data locality options, and they affect performance and costs differently. We can read data directly from the remote storage. That is very easy to set up. However, that means you spend a lot of time loading data compared to doing training. We can copy data to local storage before training, so that you will have the benefit of keeping your data local, but that means you will have to manage data manually. You have to delete data after each training and copy data again before training. Also, you will have limited storage because it's limited to local storage capacity. And we have the third option, which is to have a local cache layer. And with this option, you can use your cache layer to manage data automatically, but it is still limited to local storage capacity. The fourth option is to have a distributed cache layer. This way you will have a centralized data management system. You will have scalable cache space. However, to set up a distributed cache layer is resource intensive, it's complicated. So you will have to evaluate your options and make a decision that's best for you. Vector databases have gained popularity in recent years due to its capability to do similarity search compared to the exact match, which is used in the traditional relational database searches. And the main difference between traditional relational databases and the modern vector databases comes from how they are optimized for, the type of data they are optimized for. The relational databases are designed for traditional structured data stored in columns, and a vector database is optimized to store unstructured data such as images, text, videos, audios, and so on, and their vector embeddings. That is very useful for generative AI workloads. Okay, so let me hand it over to Alex to talk about the performance white paper.
Okay, I'm going to whiz through this. But the performance white paper is our attempt at kind of defining how to evaluate and how to benchmark storage within your environment. And mostly we focused on the common concepts for measuring the performance in terms of things like IOPS or transactions per second for volumes and for databases. Some of the things that we focused on when we started putting our thoughts down on paper was the type of pitfalls and the challenges of doing like-for-like performance benchmarking, which is and it turned out that there were typically more problems than there were easy solutions. So it's always important to understand the difference between the number of operations you need to do per second versus the throughput. They often conflict with each other, and methods to optimize for throughput often adversely affect operations and vice versa. Understanding the storage attributes that we talked about previously, like the topology and the data protection and the way you compress or encrypt your data, matters a lot, and that can dramatically change the overall picture of your performance. In most of the systems, however, latency and the way you measure latency is the key differentiator, and lower latency means better operations per second, better throughput overall. But often you also have to consider both concurrency and caching. Concurrency in terms of how many simultaneous connections, how many simultaneous clients, how many backends you can run in parallel. And caching is also extremely important to understand in terms of which layers it happens at. I've lost track of the number of times I see, performance benchmarks being published in a blog, for example, which totally exceeds the throughput of the underlying system that they're running on, and primarily that's because all you're doing is benchmarking the cache and not actually benchmarking the storage system. So without going into too much detail, the most important takeaway is run tests in your own environment with your own applications, because most of the most published performance benchmarks won't necessarily apply to your environment and might not be relevant. And with that, I'll hand over to Raffaele, who's going to take us through disaster recovery.
Thank you. Disaster recovery, my favorite topic. So yeah, I'm gonna just give you an overview of what we have in the white paper, but I really mean it when I say that it's my favorite topic, and if you wanted to talk about it, please come to our meetings, reach out to us. It's always a good way to learn from each other. In this slide, we have collected what we call the 4 archetypes for disaster recovery. In your organization, probably things are much more complex than what we see in this slide, because you have multiple applications that may be depending on each other, and then perhaps you use multiple of these techniques at the same time. But to make the topic tractable, we have identified these 4 archetypes. So from the left to the right, and also from the least performant to the right to the most performant, we have backup and restore, volume replication, transaction replication, where the database or the stateful workload is in charge of making the replication. And then we have fully distributed workloads, where again the database is in charge of replicating the transactions. And we're not going to go in details, right, on how each one of them works, but perhaps we can slice them a little bit and analyze them by some characteristics. For example, the first 3 on the left are active-passive type of disaster recovery systems. So when there is a disaster, somebody has to decide to make a switch and restart the workload or activate the workload on the passive side. While the last one is active-active, so when there is a disaster, you don't have to do anything. The system reacts to the situation by itself, and when the failure domain that was failing comes back online, the system will acquire that failure domain and have a transaction running on each of the 3 domains. Another thing that we can look at is that the first 2 are configurations where the infrastructure team can make the configuration for everyone, right? So typically, if you're using one of the first 2, the infrastructure team is the owner of the disaster recovery procedure. The 2 on the right, you see that the configuration needs to happen mostly at the database level or stateful application level. So in that case, the owner, it's typically the middleware team, or perhaps even the application team is the owner of the disaster recovery procedure. And when I explain this concept to my customers, what I try to tell them is, if you're building a platform where your applications are going to run, maybe you don't want to enforce a single approach. Maybe what you want to do is to enable more than one approach, right? And let your consumers of the platform decide what they want to use. So you should enable capabilities, and that they decide which disaster recovery procedure to use. So in the bottom here, in the bottom portion of the slide, you see all the capabilities that help you define, help you enable these patterns. Okay, in the document we talk about it in more detail. And this slide here tries to capture some more of the characteristics of these 4 approaches. I'm not going to read all of it, but let's just focus on the distributed stateful workloads, which is the most performant, is the one that I like the best, right? Where I would encourage you to really think about it and try to implement it. So again, the architectural side is active-active, so any node can take writes. The disaster recovery is triggered automatically, right? So the system recognizes that there is a problem and reacts by itself. The RTO and RPO are very low. So RPO is exactly 0 because the system is fully consistent, and RTO is seconds. Okay, you measure in seconds essentially the time that your global load balancer health check detects that there is a problem, right? Again, we talked disaster recovery ownership. We saw that it's mostly on the middleware or developer team. And then their capabilities, you may think of disaster recovery as something that you enable with storage, but in this case, the capabilities are mostly on the networking layer, right? So we need a global load balancer, and the way to do east-to-west communication. So bringing this conversation about capabilities forward, I have collected here some of the tools from the CNCF and also outside of CNCF that you can use to enable these capabilities, because they are now part of the Kubernetes set of capabilities that you get when you install Kubernetes. So you have to add some operators or other functionality to your system. I'm going to go very fast on this slide. In the document, we also talk about how these active-active workloads really work. So we go in the details of how they are built, what's their anatomy, the fact that they're based on the CAP theorem, and the fact that they use the concept of replicas and partitions, right? So replicas are typically used to provide availability, and partitions are used to provide scalability. And finally, we do an analysis of a bunch of these fully distributed stateful workloads and what they use for the replica consensus protocol and the shared consensus protocol. I will recommend, if you are evaluating these workloads, try to understand what they do in terms of these two synchronization protocols, because those determine a lot about the behavior of these workloads. And finally, we analyze we propose and describe an architecture for building these deployments in Kubernetes, because we assume that most of you will be deploying these workloads on Kubernetes. So here we have 3 failure domains with 3 Kubernetes clusters. If you distribute the workload that way, as it's described here in the picture, you get these capabilities of this ability that if you lose one of the data center, everything will keep working. And with that, back to Alex.
Yep, so without too much ado, I just want to put up a call to action. Please come and join one of our calls. Use the calls to look for advice, to talk with some of the leads in our tag, but also just to find out about different block storage systems, file systems, object stores, databases, and we have a lot of machine learning workloads and other projects who are presenting. So we look forward to seeing some of you there.
Any questions?
Hey, so I'm a current Ceph user with Rook, and I'm kind of curious about the newer projects like CubeFS and Dragonfly. Are there any major reasons that I should consider looking at those for a greenfield project?
So CubeFS is particularly exciting. It provides a shared file system with sort of POSIX semantics. And has been designed to sort of scale across both in terms of sharding and replicas with erasure coding. So we're very excited to finally have like a production alternative to things like CephFS, for example. So it might vary depending on sort of what your specific use cases are, but yeah, I would definitely suggest having a look and seeing if you can get benefits from something like CubeFS, because it might change your performance profile or your resource utilization in your cluster, for example.
So I had a question. So the 2022 survey that you showed, which showed like the top workload types that are used. Do you have a breakdown by, for those workload types, which storage type they're using? If they're using, block or file or object, is there a report that shows that breakdown?
I don't think it breaks down like that.
Okay.
But there was the latest report came out just like a couple of days ago. But normally it does not really break down, like after databases does not show lower layer, what are those?
The truth is also a lot of those systems might be able to use different types of storage or different types of deployments. So there isn't a hard and fast rule. Okay, I think we're done. Thanks everybody, and we'll be around if you have any other questions.